Okay. Good afternoon, everyone. We are sorry for the technical issue, but I think we cannot fix the issue related to with the camera, but we were able to share the screen. So welcome to today's IFAS AI and Data Science Seminar. My name is Haipeng Yu. I'm an assistant professor in artificial intelligence in animal omics science at the Department of Animal Science at UF. It's my great pleasure to introduce our today's speaker, Dr. Rohan Fernando, who is a professor emeritus at the Department of Animal Science from Iowa State University. Dr. Rohan Fernando received his PhD degree in animal science from the University of Illinois at 1984, and then continued there as a faculty member. In 1996, Dr. Fernando joined the Department of Animal Science at Iowa State University as a full professor. Dr. Fernando is internationally recognized for his contribution to the development of methodology for genetic improvement for livestock, especially in the area of incorporating molecular information into breeding. And he has received over 100 invitations to speak and teach on this development in 21 countries. And he retired from Iowa State University in 2022. Today, Dr. Fernando is going to talk about how would Fisher use genomic information to determine the genetic contribution to continuous trait. So let's please join me in welcome Dr. Rohan Fernando.
Thank you, everybody. Thanks for coming. I didn't expect so many people. So, actually, my title is kind of too provocative. How would I know what Fisher would do? I can only guess, but I'm pretty sure what he wouldn't do. So I know that many of you are involved in getting new types of data, and sometimes in very, very large quantities. And what I'm going to talk about is the new type of data that we had to analyze in quantitative genetics, which is not new anymore. And maybe it will tell you something about what you can expect. And sometimes when we get new types of data, we have to decide, are we going to analyze it the same way we have been doing before? Are we going to tweak our methods and tailor it to the new type of data, or do we have to completely adopt a different type of analysis? And I don't think there is a simple answer to that. We have to really understand the methodology, the current methodology, and the value of the new data, and then we'll have to see how to do it. And even in this case, I don't know whether what I'm going to propose, the method, the way we analyze this data is the correct way, and everybody has to decide on their own. Fortunately, all of us don't have to do the same thing, right? Some people might think this is the best way to do it. Other people might say this is the better way to do it. And as time goes on, people will adopt the best way to do things. And so luckily we are living in a democracy, and everybody can do their own thing, and then people will decide how to go about doing things. So it's not going forward. Oh, yeah. Okay, so in 1918, Fisher wrote this very important paper where he tried to show how continuous traits, the inheritance of continuous traits, could be explained by Mendelian inheritance. So at the turn of the century, Mendel's laws were rediscovered, and people were wondering whether the simple laws of inheritance that he came up with, where an individual inherits, he called them invisible factors from each of their parents, and that determined what you would see in that individual. And what people were wondering, not only Fisher, several other people were wondering, is whether this type of inheritance at several genes, not at one pair of factors, but several pairs of factors, could explain what they observed for continuous traits. Because people have known for a long time that relatives resemble each other, right? Even when you see twins, you recognize them as twins, and you recognize a resemblance between parent and offspring. And at the turn of the century, people were using the correlation between relatives to quantify that resemblance. And so the question was, can that correlation be explained by several Mendelian factors acting together? And other people had tried to look at that, and they were not quite successful. And then Fisher wrote this paper, and then things started working. So one of the things that Fisher introduced in this paper, he called that the factorial model of inheritance. And the reason he called it factorial model is because Mendel talked of independently inherited factors, invisible factors. And that's how Fisher later on, when he came up with factorial experiments, that factor came all the way from Mendel and to this paper, and that's how we have these factorial experiments, because of the word that Mendel used. So this is a very important paper. And another concept that was introduced here in this paper is the concept of the variance. Fisher introduced that in this paper, the term variance was not used before. The normal distribution was parameterized by the mean and the standard deviation, not the variance. The reason Fisher wanted to use the variance is because he observed that if two random variables are independent, the variance of the sum of those two random variables, for example, the phenotypic value, is the genotypic value plus an environment, a non-genetic part. So if these two sources of variation are independent, then the phenotypic variance will be the genotypic variance plus the environmental variance. And so he wanted to decompose the phenotypic variance into different components. And that can be done with variance, not with standard deviation. So that's why he introduced the term variance here. And you can see the analysis of variance get its start here with this paper. So before we look at what Fisher did, let's just briefly say what a two-way factorial experiment is. So you have a factor A and a factor B, and then I'm just writing a model here, very simple model without interactions, just with the main effects. So that's our model, and then if we write this in matrix notation, we can write y is equal to x beta plus E, the residual, where the X matrix has a column here with ones. This thing is really sensitive. And another column here for A1 and another column for A2, a column for B1 and a column for B2. And then we know the least squares equations, and we can fit those and estimate the effects of those treatments. and then we can test hypotheses. So let's see what Fisher had to do. So here is Fisher's model, the multifactorial model of inheritance. And again, I'm just considering the simplest form of the multifactorial model, an additive model, no interactions. So the X beta is modeling the non-genetic part, and Q alpha is the genetic part that we are modeling. And so the Q will have a column, several columns, one column for each gene, for each factor in Mendel's terminology. So, and then let's say at factor 1, there can be a big A and a little a. So, and then we count the number of big A's. So my column, my first column in Q will have a 0, 1, or 2, depending on how many big A's there are. And the same for column 2 and column 3 and so on. And the alphas are the effects of these factors. But the thing is that Fisher was not able to observe Q, right? So he couldn't observe Q. But he knew that relatives are expected to have similar genotypes, and that's why they already knew that the correlation between close relatives was higher than with distant relatives. And that's what he needed to explain based on this model. So what he did is he developed theory for the covariance between the genotypic values, this A vector. He was able to develop theory to show how this A vector is the covariance of this A vector given the pedigree. So if you knew that, okay, let's say we have 4 individuals, 2 parents and 2 full sibs, given that pedigree, he could tell, he developed theory to tell, to get the covariance matrix for this vector A. So just to, this is really fascinating to me. And so let's just go through, just to look at the covariance between an individual and his father. So here is the model for the genotypic value of an individual at a single locus. So this is a very simple regression model. First we have the intercept, and then here this letter Q represents the number of big A's at that K locus. So that can be 0, 1, or 2, and the alpha is the effect of that factor. What I have done here is I have written Q as the sum of the 2 factors that came from the mother and from the father, the maternal and paternal contribution to this Q. And this is the substitution effect. And then if you want to look at the variance of this genotypic value at this locus, that's the, since this thing is a constant, we have the constant squared and the variance of this sum, and assuming that these 2 are independent, we can write the variance of this sum as the sum of the variances. This is a Bernoulli random variable. It's either 0 or 1. So the variance of this thing is p times 1 minus p, and we have 2 of those, so that's why we get 2 times p times 1 minus p and alpha squared. So now let's look at the covariance between an individual and the father. So this is the individual and that's the father, and I have written the model for the individual and for the father. And we know that the individual gets its maternal allele from the mother. Only this paternal allele is correlated with the father, assuming the parents are independent. So when we write the covariance between UIK and the father's genotypic value, we only need to look at the covariance between the paternal allele and the father's maternal and paternal alleles. And according to Mendelian inheritance, the individual receives one of these alleles with equal probability. So let's consider the situation where the individual receives the father's maternal allele. So I have colored, this is the allele that came down from the father to the offspring. And then when we look at the covariance between the genotypic value of the individual and the father, we get alpha squared, and the covariance between the father's maternal allele and the individual's paternal allele. But since this allele is actually the maternal allele of the father, it becomes a covariance between the father's maternal allele with itself, which reduces to a variance, right? And since this only explains half the genetic variance at that locus, so that's why we get 1/2 the additive variance at that locus. And the same thing happens if it receives the maternal allele. The algebra is exactly the same, and still you get 1/2 the additive genetic variance. So an individual either receives the maternal allele or the paternal allele, doesn't matter which one, that the additive genetic variance at that locus is 1/2 the additive genetic, the additive genetic covariance between father and offspring at that locus is 1/2 the additive genetic variance at that locus. And now, if we assume that all these loci are independent, then we can get the total covariance as the 1/2 the additive genetic variance. So for that, we have to assume that these loci are in linkage equilibrium. So that was just between father and offspring, and you can do the same between mother and offspring. And using that formula, you can develop the covariance matrix for the entire pedigree, just using the parent offspring results. And those of you in genetics have done this, and should know how to do that. And and this A matrix is the additive relationship matrix. And this thing is the additive genetic variance across all the loci. And I'm only going to talk of the additive model for most of my talk. But Fisher also considered non-additive inheritance, the interaction between the two factors that come from the mother and father. We call that dominance in quantitative genetics. And also interactions across loci, epistasis. But most people don't use those models with epistasis and so on. We might consider models with dominance just to estimate the dominance variance to see how important it is. But most of the genetic evaluations, at least in animal science, in animal breeding, what we do is we use mostly an additive model for genomic prediction. So the model that we currently use for looking at the contribution, look at the contribution of the genetic variance to the phenotypic variance is this model where we have y is equal to x beta plus ZA, where Z is just an incidence matrix, because some of the individuals may have repeated records and some may not have any records at all. So that Z matrix is just there to pick out the elements of A that go with Y. And then now we can write the variance of Y as Z times the variance of that little a, which is A sigma squared A, and then plus identity matrix times sigma squared E for the residuals, where sigma squared A is the sum of the variances across the loci, and at each locus we said this is the variance. So we can get the total variance. So this is the decomposition of the total variance as the genetic variance, the additive genetic variance plus the residual. And these days, people use maximum likelihood to estimate these variance components, I suppose. packages like ASML and so on. And some people are using Bayesian methods, and that's what I and people at Iowa State have been using Bayesian recently. And then for genetic evaluation, we use the same model, and we use Henderson's mixed model equations that are given here for predicting the genotypic values that are not observed. These A's are not observed, and we predict them by solving these equations. And you can see here, we need to invert this A matrix, and fortunately, A inverse is extremely sparse. Even though A might be dense, in A inverse, there are only very few non-zero elements. And we can calculate A inverse without even looking at A. We can just from the pedigree, just by looking at the pedigree, we can calculate A inverse. For example, to invert any matrix, any general matrix, the number of computations is proportional to n cubed, n to the power 3, where n is the order of the matrix. But for calculating A, we can do it in linear time. And it, even with million individuals, it can be done in seconds. Calculate A inverse. So that's why these equations are very powerful, because we can form them very, very efficiently, and then they are solved, of course, since if in the national dairy cattle evaluation, the number of equations is millions, maybe close to 100 million or more. But still, these equations can be solved iteratively, not exact methods, but iterative methods. And so that has been the state of the art till the genomic information came into the picture. So now let's look at what happens with genomics. So now, unlike with Fisher, we can let's pretend we can observe the genotypes at the trait loci themselves, okay, just to keep things simple. So then this is our model. So we have the non-genetic part of the model here, and these are this is what Fisher didn't observe. The columns of Z are now observable. They are either 0, 1, or 2. So let's see I'm going to first explain how the genetic variance is estimated in the most popular method. And the most popular method, this is some people, we were talking earlier today about Van Reyden 1 and Van Reyden 2. So this, what I'm going to explain is Van Reyden 2. So what you do is the M is obtained by dividing each column of Q by multiplying actually each column of Q by 1 over square root of 2p times 1 minus p. That is the square root of the variance at that locus. So you are dividing by that thing. And if you divide the columns of M by that thing to go from here to here, then you have to multiply alpha also by the same thing. Otherwise, the model will be different, right? So if you multiply and divide by the same thing, you haven't changed the model at all. So M gamma is actually exactly equal to Q alpha. Okay, so the way we have done things. And let's go on. So now, remember we said that the additive variance is with assuming linkage equilibrium. We are taking the sum of the variance of the sum of the variances across loci, and at each locus, this was the variance, 2p times 1 minus p alpha squared. So now, the way we scale things, the sum of the gamma squareds becomes the total variance. And then to estimate the variance, we are going to assume that these gammas are IID normal with mean 0 and variance sigma squared gamma, then the expected value of sigma squared A is the expected value of these gamma squareds, and each gamma squared has expected value of sigma squared gamma, and and we have m of those, so that becomes the expected value of sigma squared A. Okay, so that's the trick involved in Van Reyden 2. So now if we think of the variance of m times gamma, which is our additive genotypic value, we can, since m is observed, it's not a random variable anymore. It is m times m transpose times the variance of gamma. It's actually m times the variance of gamma times m transpose, but this thing has variance I sigma squared gamma, so that's why we get that thing. And if you divide m prime by the number of markers m, then this also gets multiplied by m. So now if we call this part g, then we have g times sigma squared A is the variance of m alpha. And then we can go back to this model, x beta plus A, where A is equal to m gamma, and we can estimate the variance of y, let's say by maximum likelihood, to be from this model here, from the variance of y being g sigma squared A plus I sigma squared E, we can estimate these unknowns, sigma squared A and sigma squared E. And then we can partition. Now, what Fisher did was with pedigree. Now with genomic information, this is the most popular approach. So what we have done is we have replaced the pedigree-based relationship matrix A with a genomic relationship matrix G. Now, one thing that is important to remember is, I don't know whether you are aware of this, but G times sigma squared is not a genetic variance covariance matrix. Because as you can see here, this M is observed. So this given, strictly speaking, given this M, this thing is not a random variable. The only reason this became, we were able to write that the variance of A is equal to G sigma squared A is because we consider these gammas as random. But really, the substitution effects are not random, right? I mean, if they were random, you won't be able to do genomic prediction. Because if you estimate from some data set, and in another data set, if the gammas are random, how can you predict? So these gammas are actually not random. The treating them as random is a Bayesian idea. You know, in Bayesian statistics, an unknown, you can quantify what you know about it using a density function. You are saying, okay, I expect most of my gammas to be close to 0. Some I would expect to deviate in the positive direction from 0, some in the negative direction, and a very few to deviate a lot from 0 in the either positive or negative direction. That's what we think, and that what we think can be quantified in terms of a normal distribution. So in the Bayesian approach, you treat that as a normal distribution. But still, this A, in my mind, is not a random variable given M. And even if you treat this as random, for me, the genetic variance comes from M being random. So if M is not random, you know, for me, this G matrix that you get by treating gamma as random is not a genetic variance covariance matrix. So I think you have to be careful, even though you can estimate sigma squared A using this model, not to think of G as a variance covariance matrix. It is a matrix of genetic similarity. Two individuals that have high values for G will be more similar genetically. Basically, they have the same genes, the similar genes, but it's not a genetic covariance matrix. And if you think of this as a genetic covariance and build on that, you might run into problems. Things might happen that you don't expect. For example, the covariance between parent and offspring, you might get a negative answer. Some stupid things can happen if you think of that as a genetic covariance matrix. So I don't think it's correct to think of it as a covariance. But it's so subtle, right? Because it looks exactly what we have done before, and you can fall into the trap of thinking incorrectly. And I think it's important to, especially for students and for professors, to teach their students correctly that this is not a genetic covariance matrix. If you want to use this model, fine, but don't think of it as a genetic covariance matrix. Because if you think and if you build on that, you might end up by making wrong assumptions. So now I'm going to, but before I go to that slide, so I'm going to talk of a different way of doing things. So let's say we have a big data set and we can estimate these gammas very precisely. Then essentially we can observe A, right? Because M is observed. And if I can estimate this gamma very precisely, then A is observed. And if I can observe A, I can just go and calculate the variance among the A values. And that tells me what the genetic variability is, right? And that's the way I have been trying to estimate the genetic variance. But of course, I didn't have a huge data set. If this M has 50,000 columns, and I never had a data set with 50,000 rows. So I had to estimate gamma. And the way I did that was using a Bayesian approach. Again, sample gamma from its posterior. Given all the information, I draw a sample for gamma from its posterior. From that, I calculate A. And from A, I can calculate a variance. And I do that repeatedly. And I take the mean of all those estimates, all those sigma squared estimates, sigma squared A estimates. And that's an estimate of the posterior mean for sigma squared A given the data. So that's the approach that we have taken. And we have been doing this for over 10 years now. And I will show you how this relates to the common approach that is done here. So here we are looking at the general situation where we are not going to assume linkage equilibrium. So here is one of the elements from my A vector, a random element. And I want to look at the variance of that random element. And the variance of that random element is M I prime. So that's the row vector of genotypic values that have been scaled, and actually it doesn't matter that it was scaled, and times alpha. Should I have put gamma there? Probably, right? Because this is scaled. So I think I should have put gamma there. So then the variance of this thing, can you recognize that this is the variance? Because this is a random vector. This is fixed. So it's like if you have a constant A times a random variable X, the variance is the constant squared times the variance of X, right? So similarly here, alpha is a constant, so that's why it's alpha prime, the variance covariance matrix for M times alpha. So here what I have written by V is the variance covariance matrix for M. And since we have marker data, since we not only have this M, we have M observed for thousands of individuals, I can estimate this V from the observed marker information. And what I have done here is I have written the contribution from the diagonals of V here, the first sum here, and this is the contribution from all the off diagonals. And the reason I did that is because here we can see the contributions from the diagonals is what we saw earlier. Is the sum of those gamma squares is exactly this one. So I should have had gamma here, okay? So here, 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 all the way, and then this thing is fine. So this, so when you estimate the variance using the popular approach, you are estimating only this part of the variance. This is the contribution to the variance from all the off diagonals. This is being ignored. And so instead of calling this sigma squared A, I put VA to distinguish this part is what we call sigma squared A, the contribution from the diagonals. And this is the contribution from the off diagonals. So just to distinguish, I put VA there. So I have gone through this very fast, so I'm giving you some references for the alternative approach. The paper where we used this approach first is given here, and it was not for genomics, it was just in general. If I want to estimate not the variance in the founders, but the variance in generation 15. Then how do you do that? You know, the maximum likelihood, the usual approach will give you the generation in the founders if you have the complete pedigree. But if I just want to estimate in some subpopulation, generation 15 males or something, this paper said how to do that. And the way it was done is you sample from the posterior the whole A vector, including that generation that you are interested in. And then you calculate just the sample variance for those individuals. And you do that repeatedly, and that gives you the genetic variance for some population other than the founders. You can do that even for the founders, you know, then you only take the variance among the founder A's. So that was given in that paper. And we have been using that, I told you, for over 10 years now. And this here, what is described in this book chapter. And if you want to get a quick introduction to Bayesian methods used in GWAS and in Bayesian prediction even, this might be a good place to go and look because it gives a fairly simple self-contained introduction. And this method that I explained today is used there. And this last paper actually compares the alternative approach that I talked about with the traditional, the popular method. And in that paper, what we did is we looked at a population where there was selection going on. And with selection, what happened is that when there is selection, it causes negative covariances between the loci. That's popularly, you know, known as the Bulmer effect. So if you have a trait determined by a very large number of loci, when you start selecting, the gene frequency doesn't change much because there are so many loci, the change in gene frequency is negligible. But the variance will go down, and the reason the variance goes down is because it causes negative covariances between the loci. And actually what happens is if you relax selection, the variance goes up again. And you can do that with simulations and see, because the gene frequency didn't change, it was just changed a little, but not a lot. What changed a lot is the negative covariances. So in this paper, what is shown is that if you use the traditional approach, the popular approach, you will not observe that reduction in the variance with selection because that thing is coming from those negative covariances between loci. It only estimates the contribution from the diagonal. And in that paper, you'll see that. But what I have done next is done a simulation where I did associative mating. So I just simulated 100 loci on 10 chromosomes, that's 1,000 loci. and a population of 2,500 males and 2,500 females. And I set the variance to be 1 before mating, and this is the residual variance. And then I did 3 generations of phenotypic associative mating. So I ranked the males based on their phenotypes, ranked the females based on their phenotypes, and mated them. Not at random, okay? The top male to the top female and so on. And that will create the variance to go up. And let's see what happens when we estimate this variance using the 2 different approaches. So here is what happens. So with random mating, this is the variance. I can now this is a simulation, so I can observe the SNP effects, right? So I can calculate the true variance without ignoring the off diagonals, and it was equal to A. And if I ignore the off diagonals, it was still very close to 1. When I estimated it using the what I like, the approach I like, where you don't ignore the off diagonals, you get 0.99. It's very close to, and these, they were not significantly different. I can do paired t-tests and they were not different. And the traditional approach also gave the same answer. You know, it's very close to 1, and so everything is fine. When I do associative mating, the true variance is very high if I don't ignore the off diagonals. Just if I ignore the off diagonals, so this is just the contribution to the variance just from the diagonals, it is 1. Because I didn't do any selection, it was only associative mating that made the loci now correlated. When I estimated using the alternative approach, I get something very close to the true value, and this was not significantly different. Whereas here, I get something very different from this true value, but it's also even higher than this one. We can talk about that later if somebody is interested why that happens. I can speculate why that happens, but I don't know, I haven't tested it. So now let's look at genomic evaluation. This is the most popular method. You fit this model, the model that we had before, but earlier we said the covariance matrix given pedigree, this vector of genotypic values had the additive relationship matrix times sigma square A to be the covariance matrix. But now what we are going to do is we are going to say that this thing has variance covariance matrix G, that is MM transpose divided by M, the number of markers. But now we have to invert G. And earlier when we first got genotypic data, we only got genotypic data for about 2,000 individuals. And the number of columns in M was 50,000, so it made sense to go and do it this way. But now we have, I told you, I think in dairy cattle, it must be well over 2 million now, genotyped individuals. So even if you analyze just the genotyped individuals, we don't do that. This G will be, will have millions, order of millions, right? So you can't invert that. And actually, it doesn't even have an inverse. It's a singular matrix, because if it has only 50,000 columns and that many rows, this million, let's say it's 2 million. 2 million by 2 million matrix can have at rank at most 50,000. It can't have a rank more than 50,000. So you can't even invert it. So what people do is they will add something to the diagonal or do something to invert it. An alternative approach is to just to fit this M alpha here. Put M here, M gamma here, then you have Z times M gamma, and that's what is done. That's the way we approach the problem. So this W is just a covariate matrix, maybe with some repeated rows, and some rows are not there at all. So So this is the way we approach, and the mixed model equations are much simpler now. This thing will be 50,000 by 50,000 if you have 50,000 rows in, 50,000 columns in M. Doesn't matter how many observations you have, millions or 10 million, this will be only 50,000 by 50,000, and you don't have to invert a G, you just invert an identity matrix, which is just itself. So it's much easier to work with this thing. So that's why I think that trying to do what Fisher did and calculate something that looks like a covariance matrix doesn't, I wouldn't go there. I would just fit the, we have observed the genotypic covariance. Why don't you just treat it like everybody else would do it, rather than trying to do what Fisher did when he couldn't observe these things. And then when you do it, I think one thing you might end up calling G a genetic covariance matrix and get in trouble. And also you're assuming linkage equilibrium when you don't need to. You know, and then if there's a sortative mating or something that causes linkage disequilibrium among the loci, then you're estimating incorrect things, and it's unnecessary. So that's why earlier when we were talking, I said sometimes the new data might make our life simpler, and if you look at it properly. And so that's why it needs, we shouldn't mindlessly go and do what we have been doing before. At the same time, you know, don't just throw away what you have been doing before. You have to think about it and do it after some thought. So next what I want to do is talk a little about non-additive models. So if you want to include dominance in the model, it's very straightforward. All you have to do is, instead of just the additive effect at each locus, you also have to fit a dominance effect. So that's fairly straightforward. And actually I'm working with some colleagues in Germany on doing the alternative approach for a dominance model, and they are also, we don't have to assume linkage equilibrium, and we can partition the additive and dominance effects nicely. And so, but the problem is when you have epistasis, because when you have epistasis, if you want to model it explicitly, it becomes very complicated because you don't know what kind of epistasis to model, because there is two-way epistasis, and between which locus and which locus, between all pairs of loci, then that's lots of interaction effects to put in the model. And if you want to model even higher levels of epistasis, then there are too many combinations to look at. So this is where we have used a neural network model, an artificial neural network model, where this is the trait that we think might have epistasis. And what we have done is we have written the model for this trait as the sum of these things, where this Yij is just a trait like we had seen before, that we model linearly on the SNP effects. So the Yijs we have modeled nicely as before, and then this F is, you know, in the neural network literature, what people call an activation function. We use I think a hyperbolic tangent, and then these are the effects that you can estimate. You know, if you have just a few, if this sum is not very large, you can estimate even this by least squares. And this approach was taken in this paper, and we simulated a trait that had non-additive epistatic interactions, and the neural network model did significantly better than just ignoring those interactions. So this has been implemented using the Bayesian approach in the package called JWAS, and so that's available. And I think that's all I have, and if you have questions, I'll try to answer them. Yeah.
Can you just explain a little bit again, why the geometrics 2 times the additive variance is not the genetic variance?
Okay, I can explain. Yeah. So when you, in Fisher's situation, he couldn't observe the Q matrix, right? So can we go to that slide, Haipeng? And go. Yeah, let's even look here. So if I sample, given the pedigree, all I know is the pedigree for, let's say, 4 individuals. Like I said before, right? 2 parents and 2 offspring. So if I go and take a random sample from 2 individuals, mate them and get 2 offspring, the genotypes of those 4 individuals will be randomly sampled, right, from the population. And then this A vector is going to be, every time I sample, I'll get a different A vector. Not because gamma is changing. Gamma doesn't change from sample to sample. M changes from sample to sample. So if I sample according to a pedigree, the M will change every sample. So A is a random variable. And we can talk of the genetic variance covariance matrix of A. The variance covariance matrix of A, which is a genetic variance covariance matrix, right? Because the genotypes are in M and M is randomly sampled. So conditional on the pedigree, A is random if you don't observe M. But if you observe M, then if you say G is the genetic covariance matrix, I will ask conditional on what? So G, actually, when you calculate it, 1 read in 2, M is observed. The only randomness that we kind of artificially introduced is by treating gamma as random. So it's not a genetic variance covariance matrix. And actually, if let's say I don't have to assume gamma to be random, let's say I have 10 million observations and only 50,000 loci, then I don't have to assume gamma to be random, right? I can just do least squares. Then where is the A is fixed, given M, A is a fixed quantity. And why are you calculating the variance covariance matrix of a fixed quantity? So just because you make gamma random, that didn't make A, the variance in A is not genetic. Genetic variance comes from the genotypes being randomly sampled.
That is the variance rates coming from the gamma that is sampled from your distribution.
Yeah.
M
is
for G, you know that.
Yeah. So it's and the only reason that the variance of the gammas was the right thing is because you scaled M and then you multiplied the alphas by 2pq, and then the sum of the gamma squareds became the genetic variance under equilibrium. But if you don't assume equilibrium, it's not. And like you saw, when you didn't assume equilibrium, when you assumed equilibrium, and there was no equilibrium, you get a wrong answer. And you saw that in my simulation that I did here, and also in the paper that I referenced here in this last paper, you'll see that it overestimates the variance. Here it underestimated it, there it overestimated it, because in that paper there were negative covariances due to selection. And what I'm saying is it's unnecessary to do that, to try to calculate a G matrix. Fisher did it because he didn't observe these things. And he conditioned on the pedigree. After conditioning on the genotypes, it doesn't make any sense to calculate a genetic covariance matrix. You can calculate the covariance matrix of the A, assuming, that gamma is random, but that's not a genetic covariance matrix. Yes, you're welcome.
Any other questions? No, I have one question, Rohan.
Yeah.
I think at last you introduced we can using that like activation function, for example, hyperbolic tangent, to incorporate nonlinear like a relationship. I think some of the colleagues I think they are interested in the multi-omics integration. So I think that method may also apply to multi-omics. So can you explain to us like how we can actually do that?
I really can't explain, but Hao Cheng and some of his students, they have a paper, I think it was published in Genetics or G3, I don't know. Because I know it can be done, but I don't have it off the top of my head. They have a way to incorporate multi-omics into the picture. And actually they also have a paper where they showed that the single step method that is used in animal breeding, that also can be formulated in terms of a neural network. So you'll have to go and look at those papers. The principal author is Hao Cheng at UC Davis.
No additional questions. Yes, thank you, Dr. Rohan.
Thank you very much.